Okay, welcome to the mini course. Thanks, Alex.
Okay, great. Good. Okay, so yesterday I sort of started talking about Erdős-Hajnal and talked about just sort of small cases. And as you kind of try and prove Erdős-Hajnal for slightly larger graphs, sort of what you can say about your big graph changes, you can kind of say less. So when h is very small, we were able to kind of get a complete description of what G looked like if it was h-free. But as h gets bigger, we have to sort of change strategy a bit. Okay, so one thing you can try and do is look for kind of really big, really nice structures, and that's what I'm going to talk about today. And then the remaining two, I'm going to look at some further topics. Okay, so let's work with hereditary classes of graphs. So just rather than just h-free, let's work with a hereditary class G of graphs, and that just means that it's closed under taking induced subgraphs. So i.e. closed under taking induced subgraphs, or equivalently closed under deleting vertices. Okay. And a sort of remark that if I have a hereditary class of graphs, it's characterized by the minimal graphs, so the graphs of minimal size that are not contained. So kind of remark. So G is characterized by minimal graphs not contained in G. Maybe one thing to remark, so there's sort of two kind of quite natural notions of class that you might kind of want to think about. So one of these hereditary classes closed under taking induced subgraphs. There's another type of class that people looked at a lot, minor closed classes. So I'm not going to talk about those other than to say, so graphs closed under taking classes, closed under taking minors. Minor closed classes, this statement in brackets becomes really nice by there's a deep theorem that says actually that every minor closed class is characterized by a finite set of excluded minors. Hereditary classes are more, there are many more hereditary classes. So you can have certainly many only defined by infinite sets of excluded graphs. Okay, so sort of the kind of big and poorly understood world of hereditary classes. Okay, I mean, again, lots of people have proved some very nice theorems about hereditary classes, but there's an awful lot left to understand. And from the structural direction, they're really hard to understand. So that there isn't a nice general structural theory describing hereditary classes. Okay, so for instance, okay, H-free graphs, just a sort of sanity check. H-free graphs are clearly a hereditary class. Or graphs with no induced cycle and of length at least k, or any list of cycles you want, you could. By the way, an induced cycle is often called a hole. So if I use the word hole, that's what it means. Okay. Right. So we say that G has the Erdős-Hajnal property which I'll probably abbreviate as EHP for obvious reasons. Well, exactly the thing you expect. So there's some constant greater than 0, so it exists C greater than 0, such that every element of the class has a clique or independent set of size at least size of G to the epsilon, to the C. Okay, so it has a polynomial size clique or independent set. Okay, so what does the Erdős-Hajnal conjecture say? It says that for every H, the class of H3 graphs has the Erdős-Hajnal property. So it's just a rephrasing of the conjecture. Equivalently, it says that every proper class, so every class that isn't just everything, has the Erdős-Hajnal property. So if you're a proper class, there's something you don't contain, there's some H that isn't in your class, and now, okay, so since it's a hereditary class, you're H3. Okay, so Erdős-Hajnal conjecture is equivalent to saying every proper class has the Erdős-Hajnal property. Okay, good. Right. Let's go back for a second to this, the kind of e to the root log n bound of Erdős and Hajnal from last time, and just kind of think about what the strategy was there. So somehow the idea was you kind of find a big, divide your graph into two, take two big pieces, and in one side, okay, and you want, okay, let me say it differently. So you want two big pieces that are sparse or dense to each other. So there are a few edges, let's say, from left to right. Every vertex on the left has a small degree out to the right. So we found sort of two big pieces of the graph so that from one to the other it was sparse, or maybe dense, fine complement, and then you're sparse. Okay. And inside one side, we found a cograph. So we said, okay, find the largest cograph you can. And now I'd like to find a cograph on the other side and put them together. I just need to make sure either all the edges are there or none of the edges are there. So let's just take anything that's adjacent to, let's sort of say, got A on the left. Take anything on the right that's adjacent to anything at A. Okay, and then look at the rest of the right-hand side. Inside of that, you find the largest cograph you can, let's say B. There are no edges from A to B, so A union B is a cograph. And if the numbers work out, so if you've managed to find big pieces, it's sufficiently sparse between them, so sufficiently large pieces that are sufficiently sparse, and you can find a big cograph on the left, and among its non-neighbors, a big cograph on the right, and put them together. Okay, so all the numbers have to work out, but if they do, then by induction, you get a nice big cograph coming out. So remember, we want cliques or independent sets. We're also happy to find cographs instead, because up to a square root, that's just as good. Okay, so that was the strategy of Erdős and Hajnal. Let's sort of dare to dream that that strategy might be, as good as possible. So, what's the absolute best that we could hope for? If we could use this, if the strategy was kind of in an ideal world, what would happen? Well, okay, I'd get two linear size sets. Okay, that's the best I can hope for, linear size. And dense or sparse, let's sort of just kind of dream and say I had no edges or I'm complete. Okay, so I'd like a pair of linear size sets that are complete or anti-complete. Okay, so let's think about that. So class G, so this is called the strong Erdős-Hajnal property. If there exists, let's say C greater than naught, such that every graph in the class, okay, well, I want at least two vertices. Every kind of non-trivial graph in the class, I can find a linear size pair that's a complete or anti-complete. So has disjoint AB such that A and B both have size at least constant times the size of the whole graph, so constant fraction of the graph, they're linear size sets, and the pair AB is complete or anti-complete. Okay, so complete meaning I've got A and B and all the edges in there, and anti-complete meaning I've got A and B and no edges between them. Okay, think I talked about it yesterday, this word anti-complete is really useful because it avoids an extra sentence. Okay, good. So that's the strong Erdős-Hajnal property. Trying to reorder my notes into vaguely the right order. Okay, there's one obvious lemma that you should check. I mean, why bother defining this in the first place? I mean, it should at least be that if you have the strong Erdős-Hajnal property, you should have the Erdős-Hajnal property. And there's a lemma that says that the strong Erdős-Hajnal property implies the Erdős-Hajnal property. Okay, that's actually a sort of easy exercise. So if we have a class with the Erdős-Hajnal property, let's sort of just check the recursion very quickly. So we have a graph on n vertices. It gives us, okay, a pair of sides at least constant n. And so we're going to get the recursion. I mean, I'm going to get, how big a cograph will I get? Well, let's say I'm going to prove that f of n. Okay, I'm going to prove that we can take f of n is n to the epsilon for some epsilon, that we get a cograph of at least that size. Okay, so I'm sort of waving my hands and trying to do this quickly because it's kind of an exercise. But so you just check. I take the biggest cograph I can on the left, the biggest cograph I can on the right. Whether they're complete or anti-complete, I still have a cograph when I put them together. So what size of cograph do I get? Twice f of Cn. So I get f of n is at least that. Okay, and if I'm arguing by induction that I get fn is n to the epsilon at least, then this is at least twice Cn to the epsilon. Let me rewrite that as 2c to the epsilon n to the epsilon. We need twice c to the epsilon to be bigger than 1. And as long as epsilon is taken to be small enough as a function of c, then c to the epsilon will be bigger than half, and twice c to the epsilon will be bigger than 1. Okay, so it's easy check that you get the recurrence. Okay, so strong Erdős-Hajnals are good news if we have this sort of very nice, if we can find these huge, very nice subsets or substructure, then we're off to the races. We get Erdős-Hajnal. Okay. Right. Okay, so, yeah. So why are big cographs good? Was that? Yeah. Okay. Right. So if you have so remember, a cograph is something you can build by taking disjoint unions and complete joins. And if you have a cograph on n vertices, it has a clique or an independent set of size at least root n. Okay. And you can prove that either by a direct argument or by appealing to the fact that they're perfect graphs. But it's yeah. Good. Okay. So thank you for the question. So maybe this is a good strategy for proving Erdős-Hajnal. Let's show that there's sort of a bunch of graphs so that the strong Erdős-Hajnal property holds for H-free graphs. Okay. So then there's immediate lemma. So if the class of H-free graphs has a strong, if I can spell strong correctly, there we are, strong Erdős-Hajnal property, then H is a forest. So, okay. You can prove this, maybe even Rob will have proved it or will prove something very close to this. If you think about a sparse random graph, so edge density, for instance, log n over n. So take a sparse random graph and then just delete one vertex from each cycle. So it's sort of classical alteration method. You get a graph with large girth, and it's not too hard to check that those don't have, well, they don't have huge independent sets, but they also don't have pairs of independent sets with no edges between them or all edges between them. Okay, so there's I'll just say sparse random graphs. Okay, so you can generate a sparse random graph that doesn't have a linear size complete or anti-complete pair and has large girth, and so doesn't have whatever your H is if it's not a forest. Yeah, it was a...
Yes. A priori, is there a conjecture whether the converse holds as well? Meaning if it's a forest, then it not only satisfies the Erdős-Hajnal property, but also the strong Erdős-Hajnal property?
Excellent question. I will come back to that, so I will answer that. But okay. Right. Okay, so H has to be a forest. Right, but remember, I mean, we can always consider the complement and the strong Erdős-Hajnal property, just like the Erdős-Hajnal property, the strong Erdős-Hajnal property is invariant under taking complements. So to the taking complements, the complement of H must also be a forest. Okay, and if H is a forest and its complement is a forest, that tells us that H has at most 4 vertices. Okay, and for graphs on at most 4 vertices, actually, the stuff we talked about yesterday already does everything. I mean, you're either a P4 or you can actually be obtained by substitution from something smaller. Okay, so it doesn't give us anything new for H-free graphs. Okay, but we can also try excluding more than one thing. Okay, and that's what I'm going to be talking about today. Okay, so I'm going to sort of tell you 2 or 3 nice arguments, and that's going to be maybe 2/3 of what I'm going to say. And then I'm going to kind of go into Terminator mode for the last section and to sketch out some of the ideas from a kind of more complicated argument, but I'm not going to go into detail for reasons that will become extremely evident once I start talking about it. Okay. Right, so let's actually start with, there's a nice theorem of Bonamy, Bousquet, and Thomasay from 2015. So, okay, so we have some hereditary class. If we're going to exclude, well, actually, no, I'll say that later. So, and what is this saying somehow? This says we have to exclude something sparse. The forest is sort of a sparse graph. And then this says we have to exclude something dense. Okay, so let's think about excluding something sparse and something dense. There's this nice result of Bonamy, Bousquet, and Thomasay that says that for every k at least 3, the class of graphs with no hole or anti-hole, I'll define that in a second, of length at least k, as the strong Erdős-Hajnal property. Okay, so a hole is just an induced cycle, and an anti-hole, so sort of in keeping with this use of anti everywhere, it just means the complement of an induced cycle, induced complement of a cycle, or equivalently, an induced cycle in the complementary graph. So an anti-hole is an induced cycle in the complement of G. Okay. Usually hole and anti-hole, you ask if they have length at least 4, just to avoid them becoming cliques or independent sets. It doesn't matter here, we're only thinking about long ones. Okay, and what holes and anti-holes look like? Holes, okay, it's a cycle, it's very sparse. So there you are, you know what a cycle looks like. What's anti-hole, so I'll just draw the non-edges in red. So it's very dense, so, okay, so it's sort of everything apart from some Hamilton cycle. Right. Okay. There's a really nice proof of this. I need to tell you about one tool first. So, okay, so this is a theorem of, so this is a kind of really essential tool. So it's a theorem of Erdős from 1986 that basically says, so for any h, if I exclude an induced copy of h, then I'm going to get, okay, I may not get, the whole graph might be dense or sparse or anything in between, but I can find a big piece of it, a constant fraction of it, that's very dense or very sparse. Okay, so for every h and every positive epsilon, there's a delta such that. Okay, so now the statement. So every h-free graph let's say G contains an induced subgraph on at least delta mod G vertices, so proportion at least delta of the vertices, with density either less than epsilon or bigger than 1 minus epsilon. Okay, so in other words, it says we can find a linear size piece that's either extremely dense or extremely sparse. Okay, and note you have to have both outcomes. I mean, your graph could be your initial graph could be a clique, or it could be an independent set, and they don't contain many different types of induced subgraph. So you have to allow both outcomes in general. Okay. I will gesture at the proof. I'll leave most of it as an exercise. So this is actually now a standard application of the regularity lemma. So if you know at all about semi-reduced regularity lemma, you can prove this for yourself. I point out this was proved some time ago, 1986, when it was not a standard application of the regularity lemma. So, okay, what's the idea of the proof? So take an epsilon, so pick some small constant, eta, say, and take an eta regular partition with lots of pieces. And now, but not too many, and now let's just sort of think about the reduced graph. So I'll join with white if there's lots of edges. I'll join with, so one vertex for each blob. I'll join with, pick a better color. Something that's less close to white. Orange for very few edges, and then red for an irregular pair. Okay, and let's just note that if I have a large clique of white edges, that gives me a dense piece. Okay, how many do I need? Something like 1 over epsilon. I'll get a pretty dense piece. If I have a large orange clique, if I'm remembering my colors correctly, I'll have a very sparse subset, again, of tiny linear size, but still linear size. And, okay, red is a problem, but I don't have very many red edges. So all I need is to find some reasonably large set with no red edges, and then apply Ramsey. Okay, so there, without any numbers or any detail, is the idea. You kind of look at the reduced graph, you find a piece, reasonable sized piece with no red edges, apply Ramsey, drop to a clique, and it's either dense or sparse. Okay. Right. Okay, two things I want to extract from that. So one is just the idea. It says I fix an epsilon. That means I can drop to a linear size piece with density less than epsilon or more than 1 minus epsilon. So very very sparse or very dense. Okay, so just linear size. And the other thing is to say, I mean, delta here is some function of epsilon. And again, if you've done anything with regularity, then you know that the dependence of delta on epsilon here is not going to be terribly good. Okay, so I mean, we've applied regularity with a parameter, some function of epsilon. It's going to pass back some tower. Okay, this is going to be the dependence of constants is going to be horrible. Okay, so I'll come back to this probably on Friday. I'll just sort of say there's more to be said here, and we'll come back. But just note that this is giving us, for constant epsilon, this gives us a constant delta, but the dependence is not nice. The dependence is very poor. Okay.
There should be 3 colors in addition to red, shouldn't there? So dense, sparse, and medium, and then the medium, if you have the medium peak, you can find the complement.
I'm sorry, yeah, you're absolutely correct. I should have, yeah, okay, let's throw in another color. Medium. Okay, and a medium clique, sorry, yes, thank you, Rob. I'm forgetting. So what would a medium clique give you? Okay, so let's say H has 5 vertices, and I've got lots of regular pairs, each with medium density. Okay, and then you apply the embedding lemma. So it's not, again, not hard to find a copy of H here. Lots of copies of H there if you want. Okay, thank you, Rob. Okay, good. Right, so find a big piece that avoids red edges and then apply 3-color Ramsey. Okay, the numbers are horrible already, so 2 colors, 3 colors, doesn't matter. It's equally horrible. Okay, so let's sort of sketch a proof of this theorem of Bonomi, Bousquet, and Thomaset. Okay, so let's fix K. And so now we've got some G, some large graph G that doesn't contain a whole of length at least K, and its complement doesn't contain a whole of length at least K. So no long-induced cycles, no long-induced complements of cycles. Okay, well, we can apply Rödl. And actually, for most theorems from this point on in the literature, the first step is to apply Rödl to jump to a sparse or dense subgraph. Okay, so applying Rödl.
Your BBM is limited, or
Yes, M is equal to.
M is equal to 2.
Yeah. Okay, thank you. Is there some language in which? Anyway. Okay, so. Okay, sorry. Apologies to Stefan. So applying Rödl, we can drop to a linear size subset, which is either very dense or very sparse. And let's complement if it's dense, so we can assume that we're sparse. So applying Rödl and complementing. And we're fine to complement because the set of excluded induced subgraphs is closed under complementation. So complementing doesn't make any difference. So applying Rödl and complementing, we may assume that G has density less than 1 over, okay, I don't want to worry about the numbers too much. Let's say less than 1 over 100 mod H. Okay, in fact, let's do something even better. Let's say max degree is less than 1 over 100 mod H times mod G. Okay, and you can do that by dropping to a sparse graph, then delete all the vertices of large degree. Okay, right, so we have a linear size subgraph, and I've just assumed that's the whole graph. a linear size subgraph in which every vertex has small degree. And by small, I just mean at most some small constant times number of vertices. Okay. Right. Now, let's think about if we take some set of vertices, let's say S, and let's say... yes, I do. Thank you. 100K. Thank you. Where mod h is equal to k. Okay, so let's think about some set of vertices of size at most g over 2, so most half the vertices. And what happens if we delete them? We can look at the rest of the graph. So I'm going to there's one factor we're going to need, and then we'll get going with the main argument. Okay, so let's look at G with S deleted, and that'll break up into various components. So, okay, here we go. Okay. If I can find two sets of these components so that they're union, so I want to just divide them up into two pieces so that both sides have at least an eighth of the vertices among them, then I'm happy. I found a linear-sized anti-complete pair. Okay, note, we started by moving into the sparse case, so we're kind of making a kind of one-sided argument now. We're just going to work in the sparse case. I'm going to look for an anti-complete pair. So maybe I'll just say look for an anti-complete pair of size at least 1/8 of the graph. Okay, so if it's the case, I can delete at most half the vertices, and then look at the components and divide them up somehow so that above the line and below the line, we have at least g over 8. Brilliant, I found my anti-complete pair. Just take the union of components above, union of components below. Okay, so if that works, fantastic. Otherwise, what happens? Well, it tells us that, I mean, assuming I can't find such an anti-complete pair, there has to be one sort of big component that contains almost everything outside, or most of what's outside, and then possibly some number of little components, total size at most g over 8. Okay, so there's a kind of big bit, a big greedy bit, and then some little pieces that altogether don't amount to much. Right. Okay, so that's so there's a sort of strong kind of connectivity type property. Right, and that's everything I need. Okay, we can assume the graph is connected as well. If it's disconnected, then again, either it splits into a big anti-complete pair, or there's some small pieces that you can ignore. Right. Okay, so now let's start at any vertex. We'll call this V1, and let's look at its neighbors. Okay, there aren't too many neighbors. Okay, we have maximal degree up here. We have maximal degree only a small fraction of G. So not too many neighbors. Right, so what happens outside? I have some big components and then possibly some small ones. Almost everything is in the big one. So if I delete the vertex and its neighbors, what's left breaks up into components. So delete this bit, the remainder breaks up into components. One of them has to have almost everything. Okay, great. So for V2, I'll just pick a vertex that has a neighbor in the big component. Okay, there might be lots of choices, but somebody has to because the graph was connected. Okay, so next stage, I'll look at the neighbors of V2. Okay, maybe it has some neighbors out there as well. So here we are. V2 is going to have some neighbors. And if I look at this component, well, that will now, if I delete V2 and its neighbors, what's left maybe break up into some further pieces. But again, one of them has to be very big, and then I have some small ones. Okay, I'm going to keep doing this. I'm going to walk into the big component, one step at a time. And at least for a bit, I can do this. And always there has to be something really big, and then possibly some little stuff left over. OK. So let's think about it. Let's do this k times. V1 up to vk. So I'm just drawing the new neighbors each time, so there might be some edges back. Here we go. Here I'm at vk, and again, vk, oops, there we are. vk attaches onto the big components, and there's maybe some small components. OK, so I'm just walking into the graph. If you've seen lots of arguments and kind of graph coloring and chi-boundedness, this is a sort of a bit like the Jar-Fash path argument. Anyway, we're walking in. We've got a big component and then sort of small other stuff. OK, and now here's the clever bit. We're going to keep walking past k, but our constants can't cope with more than k vertices. So what we'll do now, every time we add a new vertex, we'll forget a vertex. OK, so I'm just going to forget. So the next step, you'll use the. So the next step, I'll forget that piece of the picture. I'll just sort of stop tracking v1 and its neighbors. I've got v2 up to vk. I'll pick my, this may add something to the right-hand side of the picture. So maybe I'll draw another picture. So my new picture is, I've got v2 up to vk. I've got neighbors of v2 up to vk minus 1. Now I have a big component that's, OK, some of this stuff plus some stuff thrown over from vk and neighbors of vk that aren't neighbors of any of these later things. And fine, I do the same thing again. So now vk, I'll pick a biggest component in here and choose, wait, let me draw that more carefully. So I've got somewhere in here, I've got a big component and then possibly some small components. So this is in, right, if we delete vk and its neighbors and all these earlier ones and their neighbors, we have a big component and some small components. I'll pick, for vk plus 1, a vertex with a neighbor in the big component. OK. If I draw this better, it'll be more obvious what I'm doing. So here we had vk. And then here we have a big component, some small ones. So I'll pick a vertex here that has a neighbor in the big one. And I just keep going. OK, I go on forever. OK, so you've got this kind of rolling window of length k, and you're sort of forgetting what happens behind the window, and once the window's passed. But always, you've got a nice induced path on the portion that you're thinking about. OK, and the observation is at some point we have to repeat. It's not an infinite graph, so we kind of run on, and eventually we'll reach a vertex that's adjacent to, or we'll hit, the big component will contain a vertex that's adjacent to one of the earlier vertices on the path, and now we can close up outside the picture. So it just sort of just works. OK, there's a little bit to check there, but that's the idea.
That
Yeah.
might not be itself an induced path, but it contains
Right, but it's got this nice induced piece of it. There'll be some sort of complicated thing happening outside, which you may be able to shortcut, but you retain this bit. OK, so that's sort of slightly proof by picture. And obviously, I've skipped a couple of details, but the key idea is that you keep this window of memory and then connect up when you can. OK. Yeah. let me show you a different proof of a weaker theorem. So I'm going to go backwards in time. So before, this was excluding long holes and long anti-holes. What if we just exclude a long path and the complement of a long path? Okay, so let's prove that, so no path on T vertices or complement of a path on T vertices implies strong Erdős-Hajnal. Okay, so I'm showing you this because this is a different proof, different type of proof, and we're going to somehow generalize it in a minute. So this is sort of warm up for something else. Okay, but again, it's a really nice proof. Yeah, okay. Okay, so it's sort of weaker, but as I said, we'll generalize. Okay. It's going to be useful to have a little reference page over here. So kind of key to the map. So I'm going to have some conventions in my pictures, so I just want to be clear what they are. If I have a square box, that's going to mean, so box is always going to be sets of vertices. If I have a square box, that's going to mean a linear size set of vertices. So linear size set of vertices, and a circle is just going to be any set without constraint on the size. So just set of vertices, possibly even one vertex, just any non-empty set of vertices. And then I'm also going to use annotation A arrows B for any type of boxes to mean that the set A covers the set B, meaning for all x in B, there is some, there's a y in A such that xy is an edge. Okay, so everybody in B is seen by somebody in A. Okay, so that just means A covers B. Okay. Right. Okay. Sorry, I almost skipped over the first step. Okay, well, you kind of know what the first step is going to be. Apply Erdős. So we drop to a linear size subset. So again, we want to prove strong Erdős-Hajnal. So we want to linear size sets that are complete or anti-complete. Let's assume we don't get them. So, okay, so suppose G is PT free and PT bar free and has no complete or anti-complete pair. Of size at least some tiny constant times the size of G. Okay, so we're assuming there's no large complete or anti-complete pair. So first step, apply Erdős as usual, and if necessary, complement. So we may assume that G is sparse. So again, apply Erdős. If it's dense, it gives you dense or sparse, linear size. Drop to the subset that Erdős gives you, complement if necessary. Again, we're excluding a graph and its complement, so we're always happy to do a global complementation. Okay, so I've got a sparse graph, and it doesn't contain PT or complement of PT. So actually, I'm going to forget about the complement of PT now. I'm just going to think about the path of length T. So I want to find an induced copy of that. Okay. Choose some boxes. So I'm just going to divide up lots of boxes. Okay. I'm not going to kind of track the constants. So I'm going to kind of hide the constants a bit, just to make the argument nicer. But you can, of course, write down proper constants if you want. Okay, so I'll generate a large constant number of boxes, just some arbitrary partition of the whole graph. just divide up the boxes into, the whole vertex set into linear-sized pieces. Okay, and what I'm going to do now is find a rainbow copy of my path. So look for a rainbow PT, meaning that each vertex sits in a different box. Okay, so this first set of dividing up into boxes is completely arbitrary. Okay. Sorry, is?
Are there T boxes or more than T?
Much more than T. Many boxes.
Some function of T.
Yes. Actually, at this point in the argument, actually, precisely for this theorem, I think T is OK. It'll be clear in a second, but the thing I'm going to comment immediately on afterwards is you need more. Yeah. OK. Right. So let's sort of focus on one box. It's got lots of. So let's say B1, and we've got B2 up to bk, some large constant k, but probably k as a t. Right. First of all, the box B1 has to see almost everything in the other boxes. Okay, if I have B1 and it misses a constant fraction of B2, then I've got a linear-sized anti-complete pair. So so B1 covers almost all, meaning 99% of the other boxes. Okay, and this is really kind of what we're using about strong Erdős-Hajnal. If I pick two linear-sized sets of vertices, I know there has to be an edge between them. Okay, so B1 has to see almost everything in every other box. Okay, so let's do this slowly. Let's start with one vertex of B1. I'm just going to put the vertices in one at a time. So let C1 be a minimal subset of B1. I'll add the vertices one at a time until I first see a constant fraction of some other box. Okay, so let C1 be a minimum subset of B1 such that if I look at the neighbors of C1 intersect Bj, that's at least Bj over, I don't really mind, let's say Bj over 3, okay, for some j. So this is a subset of B1 for some j. Okay, so I've taken some, here we are, so C1, which is a subset of B1, so probably not linear size anymore. It's some small set, and it sees well, at least a third of, let's say, B2. Okay, so here we are, C1 sees a big piece of B2. Now, it sees a big piece of B2, but if I remove the last vertex I put in, it doesn't see too much of anything. It sees less than a third of everything. And our maximal degree is small. Okay, so we applied Erdős, so we're going to assume that we're very sparse. It's very small epsilon. So C1, even with this additional vertex I added in, sees less than half of every other box. Okay, so there's at least half of each box, other than B2, that C1, there's no edges from C1. Okay, so for I greater or equal to 1, well, okay. So let's replace Bj with the neighborhood of C1 intersect Bj. And, okay, what for other boxes Bi? Let's just delete the neighbors of C1. So Bi minus gamma C1 for all j not equal to I. Okay, so this set C1 has got many neighbors, linear number of neighbors in one box, let's say B2, and many non-neighbors in every other box. Okay. Let me draw a nice picture, because it'll then be clear what's going on. Okay, so here we are. Here's B2 up to B whatever. And now I've got a set C1 that covers, okay, well, with some relabeling, it covers B2 and has no neighbors in any other box. Okay, we just shrank the boxes to the non-neighbors of C1, except for B2, where we kept the neighbors of C1. Okay. Great. So B2 now has private neighbors. Every vertex in B2 has a private neighbor that doesn't see anyone else. Okay. And maybe you've already spotted what we're going to do next. We'll just do the same argument with B2. So I sort of start growing a subset of B2 until I first have a linear number of neighbors in some other box, until I first see a constant fraction of some other box. So the sum box where I see a constant fraction, drop to that, remove all the neighbors in the other boxes. So the next step will be I'll have C1. Inside B2, I'll get some C2. So C1, well, it covered B2, so it still covers C2. C2 now, okay, let's say it was, again, relabel. So we've got some B, but it may as well be B3 that C2 covers. And then the other boxes, same picture as before. And we just keep doing this. So that's the argument. So we do this t times, we build a path. So repeat to build a path. Okay. Right. You can do a bit more with this argument. So you can do caterpillars and complements of caterpillars. So not just paths and complements of paths. So prove for T bar, where T is a caterpillar. Okay. For some reason, when I draw caterpillars, they're always asleep. There's legs waving up in the air. But that's a caterpillar. In fact, you can do subdivisions of caterpillars as well. And there's a sort of sequence of papers that do this. So the first result about paths and complements was Bousquet, Lagut, and Thomasay. And then a little bit more by Koromansky, Falik, Liebenauer, Patel, and Pilipchuk. And then caterpillars and subdivisions of caterpillars were Liebenauer, Pilipchuk, Seymour, and Sperkel. So there was a few papers. Okay, this is a nice exercise given this argument. Okay, and what I point out is we made a very conservative choice of what to do. We just said, okay, I'll start with C1 and I'll just motor out into the graph one step at a time. I could instead, at this point, I don't have to handle C1. I could start from some other block here, one of these other sets. And I could grow in here until I first see a linear fraction of somewhere else. What will happen, so either I'll get another set with private neighbors, or B2 will get a second set of private neighbors. Okay, so kind of I could end up with something like several steps. And I can keep doing it, and if I can pick the right ones to do, then just from this argument. So you don't need to add anything else in. By picking the right things, you can generate a caterpillar. Okay, so again, nice exercise to think about. What can you do just from this argument with no additional ingredients? Right. Let me tell you, okay, moment pause, just. let me tell you two theorems, two reasonably general theorems. So one is with Maria, go in the right order, me, Seymour, and Sperkel. This is 20. So F and F1 and F2 be forests. So this generalizes this quite a lot. Then the class of graphs with no induced F1 or F2 bar has the strong Erdős-Hajnal property. Okay, so this is a very slow answer to your question. So this actually characterizes hereditary classes defined by a finite number of induced forbidden subgraphs that have the strong Erdős-Hajnal property. So the lemma that we had, actually slightly stronger version of it, but again, exactly the same argument, shows that if you're going to exclude a finite list of graphs and look at the corresponding hereditary class, you have to exclude a forest, you have to exclude the complement of a forest. Okay, and what this says is, if you do exclude a forest and the complement of a forest, then you have the strong Erdős-Hajnal property. Okay, so that's a generalization of these things. And another result from a different paper. So that, I mean, this generalizes sort of paths and caterpillars and so on. What about the long holes and long anti-holes? So actually, what's a long hole? It's just a subdivision of a cycle. So hole of length at least k, it's a, I mean, induced cycle of length at least k, induced subdivision of a cycle of length k. Okay, so subdivision means you have some graph, and a subdivision means you're allowed to subdivide the edges or equivalently replace each edge of your graph with a path of some length. Okay, so again, same group of authors. Paper came out the following year. So for every h, the class of graphs G such that, again, we want to exclude something sparse and something dense, so we'll exclude an induced subdivision of H, both in the graph and in the complement. Okay, so neither G nor G bar contains an induced subdivision of H also has the strong Erdős-Hajnal property. And in particular, both of these classes have the Erdős-Hajnal property. So if you exclude these things, you get the Erdős-Hajnal property. Okay. Right. Let me say something about proof methods. I'll comment quickly on the second one and then rather more length, in fact, for the rest of this lecture on the first one. I'm going to try and sketch just some of the ideas in the proof of the first one. Okay, just sort of to illustrate what you can do with strong Erdős-Hajnal property. Right. So the second one, actually, I'll just sort of say, I spent quite a lot of time thinking about coloring and chi-boundedness and stuff to do with that, and there's sort of various techniques from there. And it turns out that those techniques do kind of, with some changes, port across, and you can kind of use them in this case. So this sort of, they turned out to be, similar ideas turned out to be useful, which was a kind of nice surprise. So chi-boundedness is when a chromatic number is bounded by some function of the clique number. This is sort of just an aside. If you have a small chromatic number, then you have a very large independent set. So you could hope that chi-boundedness and Erdős-Hajnal should be related. They're not completely unrelated, but the scaling is completely different. The sort of functions we're dealing with are very different, so you can't usually say much from one side to the other side. Occasionally you can, but usually just you're dealing with different types of scale and different sorts of behavior. And in fact, usually in theorems about graph coloring, the bound you get on chromatic number is some huge function of clique number. Okay, and actually what the truth is not well understood. So there's a sort of point that there's stuff there. I don't know why I'm pointing at that theorem, because that's a theorem about Erdős-Hajnal property. But okay, but I'm talking about Erdős-Hajnal today. Right, this though is sort of techniques related to the theorem I just talked about, but it's rather more complicated. So yeah.
About the second theorem.
Yeah.
So it contains any induced, so contains any. So I'm a bit confused about the. So it's some fixed subdivision, or it shouldn't contain any subdivision, right?
So yeah, so neither G nor its complement contains any induced subdivision. Yeah. So the Bonamy Bousquet-Thomasy result says was the special case of this when H is a cycle of length K. So this, if H is CK, then this says I don't have a hole of length at least K, and I don't have an anti-hole of length at least K. Yeah. Thank you. Right, so we're excluding infinitely many graphs. Yeah, so again, this is not contained in this, because here okay, in general, none of these graphs are forests or complements of forests that we're excluding. So we do have to exclude infinitely many, but we are excluding infinitely many things here. Okay, let me generate some running room to. Okay, so okay, I want to give you some idea of the proof of this. So of this theorem. I don't know a simpler proof. There's going to be various constants floating all the way through. So in this case, I don't just want to hide the constants, I want to bury them very deeply and not look at them at all. So I think the thing to be aware of, you should sort of, there are constants kind of hidden in another room, and kind of like a baby crying, you might just sort of hear them faintly, but don't think about it. Because at every so there's going to be sort of various iterations of things going on. We have to change the constants every time we do something, and then you have to track them through. So just imagine that constants are just constants. Okay. Right. Okay, so we're excluding two forests, F1 and F2. Let's just define a tree that contains both forests as induced subgraphs and just exclude T and its complement. Just so we can just exclude, so assume, or we may assume, we are excluding T and the complement of T for some tree T. Okay. Now, what's the first thing that we're going to do? One question for the audience. What's my first step? Thank you. Apply Rödl. Okay, and again, just to emphasize, Rödl constants are horrible, but they're constants. Okay, so I can choose the sparsity I want. Rödl will hand me back another constant and say you get that portion of the graph. Okay, so apply Rödl, complement if needed, to get a sparse graph. So why may we assume this, or? Yes. Yeah, so if I have some forest, I can always add on a new vertex join it to one vertex from each component of my forest. Now that's a nice big tree. So this is my forest F1. Okay, maybe I have a forest F2. I'll join to those as well. F1 and F2 are both induced subgraphs of my new tree. Yeah. Okay, good. Someone keeps moving these. Okay. Right. Okay, so really we're going to prove a one-sided result. So where are we? We can assume that our graph is very sparse and doesn't contain an induced copy of T. So G sparse, no induced T, and no large anti-complete pair. So this is our sort of starting point, and we're going to break that by finding an induced T. Okay, and we start out the same way as before. We just start with some blocks. Here we are, linear sized blocks. Okay, so now the number of blocks is going to be significantly larger than the size of the tree. It's going to be super exponential in the size of the tree. So let's think about some gigantic constant now. Okay. Right, and we're going to sort of do two things with our sequence of we'll do two things to blocks. So we can shrink them by a constant factor. So I'm happy to do that. And I'm happy to do that any constant number of times. And also we'll delete some. Okay, so you can think of this as a bit like taking a minor. We've got a sort of contraction and deletion of some type. But anyway, we're sort of simplifying. As we go, hopefully, we're going to be simplifying our structure in some sense. So as with a lot of these things, the idea is I'm going to start with some big unwieldy thing, and I'm going to keep shrinking, but each time I shrink, it'll get nicer in some way. So some structure will appear or disappear as I go. Mostly disappear. Okay, and remember, there's a key on the right to the pictures. Okay. What sort of structure would be good for us? So we'll find, we want to find an induced T with each vertex in a different block. Okay, and actually we're going to argue by induction on the size of T. So what sort of things would be good for us? Or what would help? Okay. So suppose I could give you some very large constant number of blocks, and suppose each block had a set of private neighbors. So previously we had this business with private neighbors, so suppose we could do that for every block. So I have a huge number of blocks, each of them with private neighbors. So the idea is that this set covers the block, but there are no cross edges there. I don't care what happens between these different sets. So edges, non-edges, doesn't matter. Okay, but I've just got there's a private cover for each set. Okay. This is really good for us because let's take my tree T. Let's delete a leaf. Okay, I've got a smaller tree. By induction, I can find a copy of that, or else one of these other things goes wrong. And now I can add a leaf. So here we are. I've got my tree, whatever it is. So I look at T minus a leaf. And now I just add on, pick a vertex here that's adjacent to the leaf, adjacent to the vertex where I want to add the leaf. And now I can add it in. And I can add the vertex to anywhere I want here. So I can certainly, if I have one of these rainbow copies of T minus the leaf, I get a rainbow copy of the whole tree. Okay. So I like these sort of, think of them as matchings. Sort of matchings from the top to the bottom. So each circle has its own square, or each square has its own circle. Okay. Right. Okay. We're going to do two things. So there's going to be one set of shrinkings and deletions that comes from, actually mostly shrinkings, that comes from patterns, which are going to be related to matchings. So we're going to use sort of this. We can assume we don't have the big matching, and this will sort of drive one set of simplifications. And then we'll do a second set of simplifications, which I promise will be much less work, that will look at where we have induced copies of T, or smaller trees. And then there'll be a bit at the end where we actually tie things together. Okay, so there's sort of three steps, and there's going to be lots of Ramsey going on as well in the middle. So, okay, patterns. Right. So a pattern is going to be some boxes, and then another set. And the idea is that there'll be sort of some boxes where I cover a big piece of the box, and there'll be other boxes where I have no edges to a big piece of a box. So, so let I, S, and T be disjoint sets of integers. Okay, so I guess formula I should put brackets around the I to make it a set, but anyway. Okay. Say that the box sequence. Okay, I should give these boxes names as well, so I'm going to call them B1 up to B, okay, some large constant. Okay, capital N. Okay, so realizes the pattern STI if there exists some subset of BI. So this is going to be a subset of BI such that xi has, okay, C's a constant fraction of Bj for all j and s, and xi misses, meaning it doesn't see, a constant fraction of Bj for all j and t. Okay, so I've got my set. And so previously we had a set where it had private, it covered one box and didn't see anything in the others. Okay, here I want my pattern to be a set up here that sees a good portion of some boxes and then has lots of non-neighbors in some others. So the boxes corresponding to S, I have lots of neighbors. The boxes corresponding to T, I have lots of non-neighbors. Okay, so any questions about the definition? Okay, I'm going to draw some.
For every I less than T equals, because each guy will either see half or you don't see half.
Yes, yeah. But absolutely. But I want to choose which. It's very important I can choose which. So this is a pattern of type, and this box. I mean this comes from some box, so it sort of sits somewhere in the order as well. So this is a pattern type. So 1, I see lots of these. 0, because I miss lots of these. I'll write an X here to indicate that that's where my xi came from. And then a 1 here and a 0 there. So there's a type of a pattern. Okay, so the type just, I read from left to right. I write a 1 if I have an element of S, a 0 if I have an element of T, and an X if I've got I. Okay, and it just sort of tells me what the shape of the pattern is. This is an ordered structure, so the boxes are in some order. I'm just sort of respecting that. Okay. That's my notion of a pattern. Okay. So consider all patterns, all possible patterns with S plus T plus 1 is at most, okay, not too large. Some constant, let's say 3 times the number of vertices in my tree. Okay, I'm thinking of all small patterns now. And for any sequence of boxes and any choice of 0s, 1s, and X's, I can say, does that pattern occur?
So the 2 T's, the T on the right is a tree, and the T, does that mean 6?
Yes, okay. Let's make this U, U, thank you, and U, okay. And U. Okay. Oh yeah, so seen and unseen. So, good. Right. So now, now I'm going to get to work trying to get rid of patterns. So, okay. So if I look at some sort of sequence of, let's say, 5 boxes, I can say, do I get this pattern? Okay, so can I pick some vertices in the middle box so that I see a linear constant fraction of the first box and the fourth box, and I miss a constant fraction of the second box and the fifth box? Okay. If I can stop that happening, I will. How can I stop it happening? I can shrink all the boxes. Okay, so if ever I can shrink by constant factor, okay, and this is one of the constants I'm hiding. So if I can shrink all these boxes by a constant factor so that this pattern doesn't appear, there's no way of getting the pattern, then I'll do it. So recursively, if we can shrink boxes by a constant factor, and get rid of a pattern occurrence, then do so. Okay, so we'll just iterate this. Note that we keep shrinking things by constant factors, so you have to be careful the constants don't become circular. But provided you kind of change your budget every time you do one of these things, you can keep control of it. Okay, so I hope it's now clear why I'm not talking about the constants. Okay, so we do this. So for every subset of at most 3T boxes and every possible pattern on those boxes, we say, can I shrink by constant factor so that the pattern doesn't appear anymore? So I can't generate this configuration. Okay, so I keep going. Okay, and then I'll apply Ramsey. So I've got a constant number of possible patterns. So if again, let's just focus on this pattern of length 5. So I've got this pattern of length 5. So for any 5 set, either it's there or it's not there, I can apply Ramsey. So either it's always there or it's never there. Okay, so I apply Ramsey for every possible pattern of length up to 3 times mod t. And you can sort of see that the constants are not going to be terribly good at this point. So there's a lot of exponentiation going on. Okay, but applying Ramsey, I may assume that every possible pattern, so each possible pattern, either occurs everywhere or nowhere. Okay, So I'm going to go on about another 8 minutes, just because I started about 10 minutes late. And, but if anyone has to leave, I won't take it amiss. Okay, so, right, so this is telling us a lot about how different parts of the graph can see each other. Okay, so let's kind of extract a bit more. So, so claim no pattern has a subsequence 0, 0, 0, 1, 0, 0, 0. Well, I want a bunch of zeros on each side. I'd like mod t zeros on each side. Okay. Why? Or mod t minus 1 will do. Well, then I can generate one of these matchings. So sort of here's the idea. I'll take, so I don't care what else is in this pattern. I've got this subsequence. Okay, and what I'll do is I'll take some widely spaced boxes. So I'll just draw them far apart. There we are. There's mod t boxes. And now I'd like to generate a matching. So, okay, I'll want to generate something that covers this. Okay, so I'll sort of think about the box just to the left here. I'd like a 1, an x, 1, 1, 1, 0, 0, 0. Okay, I can pick this x in any of the gaps. Okay, so I don't really care where the x is, so I'll just draw it below so it doesn't create confusion. Okay, so I'll choose an x in an appropriate gap, and I'd like this to be a 1, this to be a 0, 0, 0, and I've got to fill out the rest of the pattern somehow. Don't care how that goes. And that tells me I can find a set inside X that covers a big piece of this, misses a big piece of each of the others. Okay, that's what this pattern says. It says my X, wherever it is, I get a piece that misses a lot of vertices in these boxes and sees a lot of vertices in this box, the box where I have the 1. Okay, so I can extract a set that sees a big piece of this box and misses a big piece of every other box. Okay, let's just shrink so that it covers this and misses the others entirely. And now I do the same thing again. So again, this pattern is part of a bigger pattern. It occurs everywhere, though. So I can find a 0, 1, 0, 0. The other bits occur wherever they occur. There'll be some new x that covers a big piece of this, misses a big piece of the others. Again, we can shrink so that it covers the whole of this and misses all of the others. I can do these shrinkings because if I could have got rid of patterns, then I would have done it already. So this shrinking doesn't affect the existence of the patterns. Again, you have to avoid circularity, but you can. Okay, and look, we're just building a matching here. Okay, so the sort of second thing will cover that, then we'll cover that, then we'll cover that. Exactly builds a matching, and now we're happy by induction. Okay, so I'm aware I'm going very quickly. I'm going to get even faster now. So we don't have this big, long subsequence. Okay, so I can bootstrap to get no 0, 1, 0 subsequence. Okay, I'll relate this back to the bigger picture in a second. Okay, how do we do that? Well, I just sort of say, you've got all these blocks. You kind of put them together in kind of block parties. Guess I should have given this lecture a week earlier. So you have all these sort of groups of blocks. And now you do the same sort of thing on those. Okay. And what does a sort of 0 look like? Well, it's actually a sequence of zeros in the original. So a 0, 1, 0 sequence here would give something like that. Okay, I'm aware I've said that very fast. I'm just saying you can beef this up. It's not too hard. You can beef it up so that, in fact, you have no 0, 1, 0 subsequence in your pattern. Okay, what does all this amount to? So it's sort of kind of dragged you through lots of stuff about patterns. What does it tell you? So it tells you that if I look at, if I look in my sequence and I look at, I sort of start throwing in vertices from here, then my neighbors, I'm going to get neighbors at one end or the other very quickly and not in the middle. So I'm not going to see a bunch of, a constant fraction of this box before I've covered almost all of the left-hand box and the right-hand box, or at least one of them. So the portion, so there'll be some portions, so I'll take any set from one of the boxes. There'll be a portion at the end, at one end where I see a lot, almost everything, possibly a portion at the other end where I see almost everything, so kind of dense to here. One of these two could be empty. And then a portion in the middle where I see virtually nothing. Okay, maybe there's a boundary box here. But it means that with all the simplification we've done, you tend to have neighbors at the extreme wings and not very much in the middle. Okay. How do we use that? Okay. So I promised you one more round of simplification. Let me say this very quickly. So now we say, okay, actually, I do actually want to get an induced tree. Let's think about what trees I can get and where can I get them. So for any subset of boxes, you can say, do I have that tree on these boxes? Okay, so again, if I can shrink all the boxes so that this tree doesn't occur in this particular configuration for these particular boxes, I'll do it. So I'll try and kill as many trees as I can. That doesn't sound very good. I'll try and prune away as much as I can of the trees. And again, repeat. Apply Ramsey again. So for a given tree, we can assume, given an ordered tree, we can assume either it occurs on every choice of boxes or it doesn't occur at all. Okay, so it's the same, you have to go through a whole process there, but you attempt to get rid of trees. If you can, you do it and repeat. Lots of constants hidden in the back room. And now for each configuration, either it occurs everywhere, very robustly, so I can't shrink and get rid of it, or it occurs nowhere at all. Okay, so now we have this kind of nice structure. Now we can actually make the argument, and this will be quick. So I just look at the biggest tree I can grow, rooted tree I can grow starting from the left, and the biggest rooted tree I can grow starting from the right. Okay, so I've got a TL and a TR. My trees are going to be reasonably fast branching, so I don't need to worry about the width. I'm just sort of thinking, what depth do I have? How deep can I get them? They're going to branch nice and well. Okay. Right, so if I think about a sequence of boxes, I'll get, so I've got these, I think let's make TL look a bit bigger. So I've got something that starts from the left, something that starts from the right, and I can get lots of copies of both. Okay, so I keep taking disjoint copies for as long as I can. I must actually cover almost everything, otherwise I could have shrunk and got rid of all the copies. Okay, so this I'm just going to think of as a nice unit, and then I'd like to, okay, what will make me happy if I can build a bigger tree on the left, or I can build a bigger tree on the right. So if I can tie together a bunch of these left-hand trees or a bunch of these right-hand trees. Okay, so here's another kind of these broken guitar-like objects. And how do the edges go between here and here? So remember, we don't have this sort of 0, 1, 0 subsequences. So that tells us that if I take these blocks, I'll tend to get edges between ends of these. I don't know which ends will work. So it doesn't tell you directly. You have to do a little probabilistic argument to make it work. You need to do some random selection. You can essentially ensure that the first edges that appear as you sort of go through these trees, here and here, are an edge that joins one end of this to one end of this. Okay, so what could happen? It could be that we get something from there to there. So we start generating these, and fairly quickly we could have covered a big piece of that. Fantastic. I'll do the same thing again. I'll have, okay, and you have to take a lot on faith here because I'm skipping all the details now. So if that happens, you can do it again, and do it again and again and again. And look, I've got a TL and a TL and TL, and I've got a whole bunch of them. So these are all TLs, and I've tied them all together from the left. Okay, so I built a bigger tree. Great, I'm happy. I'm building a bigger left tree. Similarly, if right attaches to right, then I build a bigger right tree. Let me get this right, if right attaches to left, then, okay, on the right-hand side, I'm tying together a bunch of TLs. Great, that gives me a bigger tree. There's a problem. If I join the other one, I'm going to get a bunch of TRs, but on the left, so if left joins to right, okay, you can fix that, but it requires an additional argument. There's a little bit of dancing you have to do to make it work. Okay, so for apologies with the accelerating presentation as it went to the end, that's a kind of quick sketch about that argument. And I'll move on to other things on Thursday and Friday. So.